everyone, this is Mrs. Musoff here. Today we're going to be talking about solving logarithmic equations. And the methods that we're going to use are very similar to solving exponential equation methods. There are two methods. One's easier, but it doesn't always work, so that's why it's important that we know both methods. Alright, so the first method for solving a logarithmic equation is the exact same as the first method for solving an exponential equation, and that's to get logs with the same base. Alright, now for these types of problems, for example, that would mean on both sides of the equations you have a log with the same base. So let's say log base 5 of x equals log base 5 of 7. Alright, if the equation has a log with the same base on both sides, that means you can just cancel out those log bases, and whatever you're left with is your equation. So in this case, that would be x equals 7. And I'd be done. Alright, this method is the easiest method, but it doesn't always work because you don't always have a log with the same base on both sides of the equation. So that's why it's important that you know a second method. And the second method, same as with exponential equations, is to rewrite. And by rewrite, I mean go from logarithmic form to exponential form. Alright, to show you an example of that, let's say I have an equation like log base 2 of x equals 5. Alright, in this equation, I don't have a log base 2 on both sides, so I can't just cancel it out. So instead, in order to solve, I'm going to rewrite this log form into an exponential form. And remember, the way we do that is we start with the base, so that would be a 2. And then I tend to use the circle method where I just kind of use this circle to tell me the order to go in. So I start with the 2, that means the next number, my exponent is a 5. And then the answer is what the argument of the log is, so that'd be x. So by rewriting it now, I have 2 to the 5th equals x. And that means x is basically solved for. I just need to figure out what 2 to the 5th is. And 2 to the 5th, that would be 32. Okay, so these are our two methods. Again, nothing too crazy. If you felt good about rewriting from a few days ago, or a few lessons ago, I should say, then, solving shouldn't be too difficult either. There is one little exception that makes solving log equations a little more complicated than solving exponential equations. And that is you have to check for extraneous solutions. And we did this last chapter, checking for extraneous solutions, when we solved radical equations, right? Because sometimes the solution we got didn't end up working. And the same thing could happen with log equations. And the main reason for that is because you cannot have negative numbers inside of your log. You cannot have negative numbers. And by inside the logarithm, I mean like as the argument, right? So the part that usually is in parentheses. Alright, it's not in the domain of a log function. If you think back to when we talked about domain, log functions now have a restricted domain also. You cannot have negative numbers inside the logarithm. So that means when you're done solving, you're going to plug your answer back in. And if you end up with a negative number as the argument or inside the log, then it's not a real solution. Okay, so that's just kind of an extra step we're going to have to do with all log equations. And it's log, it's right, a common log, natural log, no matter what the base is, anytime it's a log equation, you're going to have to check your answers. Okay, so let's try a couple examples and you can see what we're dealing with. Alright, so let's start with these first few. Let me just add a little space in here. Okay, so it says, example, solve the equations, check for extraneous solutions. Alright, and you can tell, for example, these first two are both log equations because there's a log written down. Alright, it's pretty simple. So for number 1, it says log base 2 of x equals 3. So to figure out which method you're going to use, you want to look and see if there's a log with the same base on both sides of your equal sign. And here there's only a log on one side, so that's how I know I can't use method number 1, which means I'm going to have to use method number 2, and that's to rewrite it. So to rewrite this, I'm going to start with my base, then the exponent, and then the answer. So this will look like 2 to the third equals x. And since x is by itself now, alright, that means I've already solved for x. All I need to do is kind of simplify my answer. We don't like to leave our answers as 2 to the third when we know what 2 to the third is. Alright, 2 to the third, that's 2 times 2 times 2. So that would give us 8. So my answer would be x equals 8. But before I circle it, I'm going to check. And actually, I think these are a little easier to check your answers with, because all you're checking for are really that you don't end up with a negative inside your log. That's the only thing that could mess up your answer. So by checking, I'm going to plug this 8 into my log equation. And because that number is positive, or not negative, I guess I should say. Although actually, no, it does have to be positive. That's how I know that this answer works. All right, so then I can circle it. I can say, yep, x does equal 8. Okay. All right, let's try another example. Number 2. So we've got log base 5 of x plus 1 equals log base 5 of 2x plus 7. So these equations, even though they look more complicated, they're actually easier to solve, because this is an equation where there is a log base 5 on both sides of the equal sign. And when there's a log with the same base on both sides, we can cross that log out. And that means all we're left with is an x plus 1 on the left side and a 2x plus 7 on the right side. So now this is just a linear equation that we should be pretty good at solving at this point. All right, I'm going to get my x's on the same side, so I'm going to subtract this x just to keep the x's positive. I'm always a fan of that. So I get 1 equals 2x minus x is just x plus 7. And then I'll move the 7 over, so minus 7. And I end up with negative 6 equals x, or x equals negative 7. Or sorry, negative 6. All right, now again, before I circle that, I'm going to check my answer. And again, that means I'm just going to plug this in for x, so log base 5 of negative 6 plus 1. And then on the other side, log base 5 of 2 times negative 6 plus 7. Squeezing it in here. All right, and I'm not even going to use my calculator to check, because again, I'm just checking to see if I end up with a negative in these parenthesis pieces. And that's math that I can do without my calculator. Like negative 6 plus 1. I know is negative 5. I don't need my calculator to do that. Okay? And the fact that I end up with a negative number here right away tells me that this cannot be an answer. All right? You don't even have to finish. You can, and you can see that, oh, 2 times negative 6 is negative 12 plus 7 is negative 5. You can see you do end up with the same thing, but because it's a negative inside your log, this answer still wouldn't work. So because of this right here, that's a negative number. All right, that's why I would say, oh, x equals negative 6, not really a solution. And since that was the only solution we found and it doesn't count, we would say no solution. Okay, so that's the extra tricky part with logs, just something to look out for. All right, a couple more examples just to make sure we're understanding this. All right, I wanted to do a slightly more complicated version of that second method, so that's what number 3 is. And then an example with a natural log, just to make sure we understand how those work too. Okay, so for number 3, we have log base 4 of 3 minus x equals 2. So again, which method are we using? Well, there's only a log base 4 on one side of the equation, so that means I have to rewrite it. All right, so to rewrite this, I'm going to start with my base. Again, that circle just sometimes helps keep track of the order. So 4 to the second equals 3 minus x. Sometimes people get stuck at this step because they think, wait, I want to solve for x, but there's still this exponent here. But remember, 4 squared, that's something you can simplify. 4 squared is just 16. All right, and sometimes just by simplifying that now, it's like, oh, I know how to solve this equation. All right, so to finish solving, I'm going to subtract 3 from both sides. I'll end up with 13 equals negative x, and then I just have to divide both sides by negative 1. So I end up with x, I'm just going to switch the order around here, but x equals negative 13. Whoa. There we go. Oops. I guess I shouldn't circle it yet, right? Because we do have to check our answers. Right? Every time, make sure you're checking. It can be just a quick, like, plug in your head and check. As long as you've checked, because you don't want to say the answer is whatever, when the answer should really be no solution. Right? So really make sure you're doing something to double check. All right, so negative 13. A lot of people, when they get an answer that's negative, they immediately think it's not going to work. But that's not necessarily the case. It's not whether the answer is negative, it's whether when you plug it back into the equation, this piece, the part in parentheses, it's whether that number is negative. Okay, so when I plug negative 13 in and I get log base 4 of 3 minus negative 13 equals 2. Well, 3 minus negative 13, right? A minus negative turns into a plus. So that's really positive 16. And so the fact that we ended up with a positive number means, all right, we're good here, and I can circle it and use that as my answer. Okay. If you wanted to really double check that you did your steps right, you are welcome to type this into your calculator, log base 4 of 16, using change of base, right? Log of 16 divided by log of 4, or if your calculator is able to do it under that math option. And then you can really double check that it does equal 2. But the only reason that that left side shouldn't equal the right side is if we made a mistake somewhere. Extraneous solutions would really only come from having negatives inside the logarithm. All right, let's take a look at one more example then. Number 4, and I did slightly change it, so if you wrote it down already, take a look. I made it x plus 7. That wasn't magic. I paused the video and changed that number. So just make sure you're using that same number so you don't get confused later. All right, number 4 uses one of our special logarithms, the natural log. Remember, ln. Okay, this symbol right here, that's ln. It stands for natural logarithm. And that's a logarithm with a base e. Okay, so if you ever saw a natural logarithm in an equation, you're welcome to just kind of remind yourself, oh, that's right, that's a base e. You could even kind of put it down there as like a side note to yourself if you needed it, or you could just think about it in your head. But a logarithm, or a natural logarithm, is just a regular logarithm, but with a base e. All right, so for this equation, since there's a natural logarithm on both sides, I can just cross those out and set the rest equal to each other. 4x minus 5 equals x plus 7. And now this is just a regular linear equation, so I can solve it my normal way. So I would subtract x from both sides. I'm going to get 3x minus 5 equals 7. Add 5 to both sides. So 3x equals 12. And that means I end up with x equals 4. And again, before I circle it, I'm going to check my answer. Remember, for extraneous, you're really just checking that what's inside the log is not negative. Some of that. So I want the natural log of 4 times 4 minus 5. Really, I just want this part to not be negative. So again, I'm just going to do it in my head. That's 16 minus 5. That's 11. So we're good there. And I'll check the other side. X plus 7, so that'd be 4 plus 7. That's also 11. So I'm good. So x equals 4 is my answer. All right. Hopefully those examples helped you out with solving logs. If you have any questions, just make sure you write them down. Thanks for tuning in.